Hey, I'm Dr. Forringer. I've got a couple of research projects I'm interested in working on this semester with students. We've already started construction of a 4-axis 3D printer. This 3D printer is really interesting because the bed rotates like a record player, and the print head also rotates, so you can make really interesting shapes, and it's just a unique style of 3D printer. We've already started this project. I've got one student who's already working on it, but it's not functional yet. We need to configure the software that runs the printer and also figure out the software that creates the program for where the printer should print. So I'm looking for 1 or 2 students who either have some experience with programming or experience with CAD or are willing to learn. The next thing I was interested in looking at this semester or next semester, I do a lab in 1111 where we see how a BB travels through a fluid, and the textbook says that for these BBs moving at these speeds, a certain formula should predict the force, and it doesn't. So is the textbook wrong? Let's do some careful measurements, maybe try a couple of different formulas to see how the force depends on the velocity, and I'm looking for really any physics or engineering student, and I think this could possibly be a short paper. There are magnets inside the plastic, and obviously the like poles are facing each other because they repel, and that's fun to play with all by itself, but this particular configuration of magnets is unique, and hopefully we'll get to the point in the video in just a second. It's the next time. Here we go. If you push them close enough, they actually stick together and snap together, almost like fusion in atoms. When they're far apart, they repel, but when they get close enough, they attract. I'd like to get a student to help me take some careful measurements. I've got a model we can do, a numerical model we can do to fit the data, and again, I think that could be a short paper.
Hello, my name is Al Walters, and the only project I'm working on right now is developing a low-power GPS sensor for turtles. Motivation for that is that the commercial versions cost a minimum of $1,000, and not talking about the additional money for supporting software. So the plan was to use an old prototype that was developed by 2 professors, and it uses a Mini Pro Arduino, and it uses low power by removing a solder joint, and this is part of the thing that you attach to the turtle, and the finished thing looks like this, encased in a rubber waterproofing with a power source and antenna here. And the first version of this was to duplicate the development of this object, and the disadvantage is that it's no longer being made. So my plan going forward is to basically start from scratch, investigating the new boards that have the capability of using the USB internet connection or can transmit via the internet. And the project will involve some basic electronics and soldering and coding in Python. And I'm looking for any students, biology majors, whatever, who are interested in this, or engineering students who wants to do cross-platform development.
Hi, I'm Dr. Moffat, and I'm at UNG Gainesville, and I do research on extragalactic astrophysics. So specifically what I study is essentially the growth of galaxies over time. As you can kind of see depicted in this picture here, galaxies, they start off very small in the early universe. They actually collide and interact with one another to eventually kind of work their way down and form bigger galaxies like the galaxy we actually live in today, which we call the Milky Way galaxy, and it's a spiral galaxy like you can see in this picture here. So I do a number of projects that relate to galaxy structure, specifically measuring quantitatively properties of the structures of galaxies, because as you can see, it's pretty complicated. So it's sort of a difficult thing to quantify. So that's one of the things that I work on, is good ways to quantify the actual structure of galaxies. to be able to compare galaxies to one another fairly. Also, I look at sort of the even bigger picture, so how these galaxies are arranged in the universe on the biggest scales, because that tells us essentially how likely they are to interact as well. So those are kind of two main threads that I have going on. So you could, if you are interested in this kind of thing, could be working on that really, really big scale structure. So quantifying the structure of the universe on the absolute largest scales that we know about, or about the slightly smaller scale of understanding how galaxies themselves are put together and again kind of assembled over cosmic time. Now, to do that kind of work, as you can probably imagine, there are opportunities for telescope observing, including with our local telescope up in Dahlonega, and also using data from really, really big telescopes that are located in places all over the world. Also collaborating with big international teams, because modern astronomy is very much a data science, and I generally do this as a part of large-scale galaxy surveys. So there's opportunities for collaborating with people all over the world with this kind of stuff. And again, because astronomy is a data science, if you're interested in these kinds of projects, you will essentially need to develop some programming skills. And I think those are very transferable skills these days. Even if you're not interested in a job in astronomy one day, they are transferable skills to all kinds of data science type jobs. And that's all.
Hello everyone, my name is Long Pham. Recently we've been hearing a lot about smart devices. So what if the windows in your home can think for themselves? So I work on a material called vanadium dioxide, so that's VO2. So it is a smart material, but it acts like a light switch. But unlike a light switch that flips on and off the electric current, this one flips on and off the thermal heat that gets transmitted through. So what if we coat your window pane with this material? So here's your window pane. And we have a thin coating of vanadium dioxide. So the idea is that when it's cool outside, it allows the sun's heat to go through to warm up your room. But when the window hits a certain temperature, at this moment in time, it's about 70 degrees Celsius, the atoms in this material literally rearrange themselves. It changes from a transparent insulator to a metal that reflects heat back. So in this case, heat is being reflected back into the outside. So my research focuses on how to make this vanadium dioxide and how to test it. So the method that we use to make this vanadium dioxide is the Sol-Gel method. So think of Sol-Gel like very precise cooking. We start with a liquid chemical soup. So that would be the solve. Trigger a chemical reaction that changes it to a gel, and then use this gel to coat the glass. After firing it in a furnace, we have a high-tech thin film. So how do we know if this thin film works? Well, at this moment in time, we don't. So what we do is we characterize it. So what are some methods that we can show that it works? We can use X-ray diffraction that looks at the positions of the atoms to make sure that they're in their correct positions. And then we can blast it with lasers, and we can measure the amount of heat that is being transmitted or reflected. So by perfecting this cooking method, we hope to change this temperature down to something more reasonable than 70 degrees Celsius. So to create high-tech windows that would reduce the cost to run your air conditioners and fight climate change. That's it.
Nice.
Hello, I'm Reddy Seleshi. My research area is in water resource engineering, hydrology, and stormwater management. We've conducted some study here on the Gainesville campus at the Tumbling Creek, which is located here on the Gainesville campus. We've conducted some water quality studies like turbidity, conductivity, and dissolved oxygen. We've presented a conference presentation. I have also conducted, I have completed some design projects, engineering design projects with students in the past as well. We've presented some of our results at different conferences as well.